in CQ. And then in June of 2020, Bob and I had the article multi-band off-center field dipoles for 160 and 80 meters. And then in the December issue of CQ, that just came out, we have a simple dual band upgrade for your 40-meter dipole that was published. And Bob and I just got a preview of the January 21 issue, and that's going to have our article on balun basics. What's a balun? Why a balun? How do I make a balun? And excuse me. And then we have two articles that were accepted by QST. One is the portable 40-meter beam, which is basically a take on a refinement of the 40-meter beam that we've been using at Field Day all these years. And that'll be middle to late this year. And the second one that we did with help from several members of the club to get it measured out and working right. Portable 20-meter phase dipoles. That'll be in late 21 or early 22 with QST. And I'd like to make sure that we thank everybody if I can remember them, but I know that Frank, KC1HSC, and Colin, and Bonnie, and Allison, and Steve helped us test this antenna, and it worked out really well. It's a really cool antenna. We hope that we can use that for Field Day too, because it's really got some significant gain and wonderful front to back ratio. The next one we're working on right now is a multi-band end-fed with no RF feedback. We're trying to work on that. We just put the first test project up in the air yesterday, but we had some problems with all kinds of things, but a lot of it to do with getting the wires together and all that. And I broke an antenna, so we'll get it. Anyhow, so the outline of what we're going to talk about is what is gain. We're going to talk about ground, which is the universal reality, because everything is affected by the ground. And then what's NVIS, a near vertical incident skywave, and how do you do that? And then we'll talk about a vertical antenna compared to a dipole. We're talking about dipoles primarily. And then how does it compare to a beam? And then questions to ask when we're talking about antennas. And then that will lead to antenna specs and advertising a little bit. But primarily the talk now is about, does my dipole have gain? So what is gain? It's gain with respect to something else. And so we need a reference. Gain over what? Over your antenna, over my antenna, over vertical, over whatever. The way that's done is we have an imaginary antenna, which is a point source radiator, which of course is impossible to make, but nonetheless, if we think about it, we can write some equations for it. But we put it in free space so we don't have interference from the ground. And it's called an isotropic antenna. And it produces 0 dBi, which is whatever it radiates is 0 dB. So that's our reference point. And you put an I after it to say it's isotropic. And that's basically where we start. So antennas that you see are usually referenced in dBi, but dBi doesn't tell you how it's going to work on the ground, and that's one of the stories of this talk. Bob, hop in when I screw up, will you?
Everything's fine so far.
Thanks. Yeah. How do we get gain? We get gain by putting the energy where we want it. That means we focus it. That means we take the same power we put into an isotropic antenna and direct it where we want it. Gain is the energy that goes in the direction we want it compared to the energy in all directions. So you take something that radiates all over the place, equally in all directions, and then you concentrate it, and that's how you get gain. And every antenna that gives you gain, you put energy somewhere and you take it away from someplace else. And of course, one of the things you don't want to do is you don't want to have your energy going straight up unless you're working satellites. I mean, there's reasons for it going straight up or doing something else like NVIS. So actually, that's what a dipole does. A dipole actually focuses the energy in some directions and takes it away from others. And therefore, over an isotropic antenna, a dipole has gain. So now we might as well just go out drinking because we're done. Well, we're going to ask the question, how? And we put our lowly dipole up, and we put it in free space to start with. And we can model it in free space. There's equations that we can write that show us how it works. And what it does is it creates a toroidal pattern in space. So on the right, there's a picture of a dipole and what the pattern would look like in 3 dimensions looking at it end on. Look at it in the direction we are. If you look at it end on, it's on the right. If you look at it in the broadside, which is the way we're looking at it in the 3-dimensional picture, it looks like that. It's got lobes. So it squeezes the sphere from the isotropic antenna. It squeezes that into this, which is maybe my mouse works, into this right here. And the gain over an isotropic antenna is 2.15 dB. So it's 2.15 dBi. That means reference to the isotropic antenna. Now we have to face reality, and ground is our universal reality because that's where we are. We're not floating around in space. So height over ground affects everything. It affects the impedance. Hopefully it's 50 ohms. It affects the takeoff angle, the angle of maximum radiation. And the curves below show you that. I'll point that out in a second. And it affects the gain. For example, we go down to the bottom right. This is a 40-meter dipole, for example, or an 80-meter dipole that's either 131 feet high or the 40-meter dipole that's about 70 feet high. And it has 7.7 dBi at an angle of 25 degrees, which means that it does a pretty good job getting your signal out closer to the horizon, which, as most people know, is good for DX. And then if we're not that high, we find out that the antenna has gain that's mostly in this pattern that's vertical. But it's quite broad. These are the 40, so it's about a 90-degree sweep. And the lower it goes, the more it goes vertical. So here it's at 21, whoops, what happened? I lost it here. At 21 feet, 40-meter antenna, straight up 6.38 dBi, that's dB over the isotropic antenna in space.
Bob, can you comment on what direction the wire is headed in the bottom straight line?
These are all horizontal wires. You see the little dot? You're looking at it end on.
We're looking at it end on.
Okay.
So the arrows are pointing broadside.
Right. The arrows are pointing broadside to it. Except this one, it's going straight up. But it's still broadside. So we're looking at it on the end. So let's go on and look at it in more detail. And for those people who like a lot of numbers, here they are. This shows the height of an antenna with respect to its wavelength above ground. These are in wavelengths, fractions of a wavelength, up to 4 wavelengths out to free space. And this is what it would be for 80 meters and 40 meters. And so at 0.15 wavelength, which is 40 feet off the ground, or 21 for a 40-meter antenna, we have 6.38 dBi, and the maximum gain is 90 degrees, which means it's straight up. Gain at 25 degrees, which is good angle per DX, is minus 1.04. So there's a couple things that you can learn for this if you just go down the chart. Let's start with the far right. Notice that none of these are 50 ohms. None of them are actually 75, except for one that gets pretty close. So the fact of the matter is, the antenna impedance is not necessarily what you think it is. It's going to be what it wants to be because the ground is affecting the impedance of the antenna. And if you want to look at it with respect to its maximum takeoff angle, there's a couple of things that are worth noting. One of them is, one is most notable, and you may have heard this, you may have heard him saying this, you really want your antenna a half wavelength above the ground because, and here's the answer, one, if you look at the gain and the takeoff angle, the gain is 7.86 dBi at a half wavelength, and the takeoff angle is 28 degrees, which is pretty darn good for DX. And if you look, putting it up even higher to 1 wavelength, which happens to be 260 feet if you've got it for an 80-meter antenna, you only go up 0.07 dBi. So this is kind of a good place to be if you can do it. For 40 meters, you might be able to get away with it. You might be able to get 70 feet, 68 to 70 feet, something like that. It's not so bad at 50 feet either. And 50 feet's another good number. There's 39 degrees and 6.39 dBi is not too shabby. The takeoff angle at 25 degrees for DX has still got some gain, 5.19 dBi. So the dipole is not such a bad antenna, especially if you can get it off the ground. So anybody that's working DX with the antenna, for example, a 80 meter antenna at 40 feet, you're doing pretty darn well because you're not working at the optimal point. In fact, at 25 degrees, you're less than an isotropic antenna, so you're not getting so much out of the antenna. You're losing a bit. You're losing about 4 times the power. Okay, NVIS. This is the one Bob will tell you burns me up. Because all these people, I sometimes serve as net control for the ARES drills on 80 meters. And I've had more people come on and say, I need to talk to somebody NVIS on 80 meters, on 75 meters. And I say, if your antenna is less than 75 feet, you're an NVIS, folks. And they all want to lay their antenna on the ground because it's going to be better for NVIS. Well, I got news for you. It isn't. It ain't necessarily so. So you got to look at the patterns before you know what's going on. Let's take a look at the pattern on the right, which is the maximum gain. And you can see that its maximum gain is at 51 degrees, but at 90 degrees, it's only down about a dB. So this is pretty much a pretty good NVIS antenna. And for 40 meters, it's 40 feet. These are kind of reasonable heights, folks. So if you can't get your 80 meter dipole up higher than 75 feet, you're NVIS, period. Some people say it's a little higher than that, but we give it a 1 dB loss as a good point to be. And besides, these heights are reasonable. So if you look at the shape of the patterns, you see they're very egg-shaped. These are, again, looking at the end of the antenna. You can see down at the bottom, that's the end of the antenna. So this is what it would look like as you look off the end of the antenna. Okay, so that's NVIS. So don't think you have to put your antenna a foot off the ground, because what you're doing at that point is heating the ground up. You're not going to radiate a lot. You're basically going to be melting the ground and melting the ice underneath it this time of year. Let's look at a vertical. Better for DX. It ain't necessarily so. Why? Well, I had an antenna that I was in QST about, I don't know, 10 years ago that I talked at a club meeting before I sent the article into the RRL. And that has a takeoff angle of 26 degrees, which is pretty darn good. And at the time, I had a dipole facing the wrong direction, so it was pretty good for DX because the dipole was terrible. It was not working very well into Europe or anywhere else. So the vertical did pretty well. But the gain is minus 0.26 dBi. That's not good. But somebody would say, but verticals are great for DX. That's what I heard. Well, let's have a shootout between a vertical and a dipole. And we start down here with the pattern. This is a 40 meter vertical, 10 feet up. Pretty good. This is my vertical for 40 meters. This is what the pattern is. It's about 0 dBi is out here, so you can see it's minus 0.26. 40 meter dipole, 68.8 feet high, has 7.7 dBi at the same angle as the best takeoff angle as the vertical. So that looks pretty good. So let's look at what would happen. Let's kind of put it all together. But a dipole in the middle of the country, say St. Louis. The dipole is oriented north and south. It's 40 feet up, which is what most of us can do with the trees around here easily anyway. A little more difficult to get at 60 and 70. It's very good within 400 miles in all directions. It's down only 4 dB north to south direction, which is an NBIS, makes it a good NBIS antenna. Because that low, it actually sends basically in a circle, so you only lose a few dB, less than an S unit in the directions off the end of the antenna. The dipole has 4 dB gain over the vertical east-west at 26 degrees. Well, that's pretty good. If I want to work DX, I could probably do that pretty well with the dipole versus the vertical. It has 6 dB gain over the dipole north-south because that's the way it is. So the vertical works equally well, though, or equally badly in all directions. The answer, of course, is using 2 dipoles at 40 feet, 90 degrees apart, and they'll beat the vertical in all directions for both local and DX. So as a good universal antenna system, put 2 of them up. I have 2 antennas up. They're 80-meter dipoles. They're about 40 feet up, maybe a little higher. Actually, quite a bit higher. One of them is about 70 feet up. And I can just switch to them and get the best signal in all directions. And many times, it beats my hex beam. The patterns below kind of tell the whole story. As you can see on the left, the 40 meter at 51 degrees. This is the maximum takeoff angle. So again, these are 40 feet up. The dipole looks like this. It looks almost a circle. There's the 4 dB loss. This is east and west. That's north and south. There's 4 dB loss north and south. Not too bad. Less than an S unit. And then the other way, it's pretty darn decent when you're looking at it in the east-west direction. And this is what the vertical looks like. So you've got a pretty good chance of doing well with a dipole over a vertical in almost all applications, especially if you can put 2 of them up. 2 dipoles up at 90 degrees, you'll do great. Now, let's ask the question, let's put a beam up. And this talks a little bit about what our 40-meter beam does for us at field end. Although we don't have the separation here. We don't have 20 feet separation. We only have 10 on the 40-meter beam we use. But if we take a 2-element beam, this is a 20-meter beam, and look at it, what's our pattern look like? Well, at a half wavelength up in the air, it's 10.88 dBi at 26 degrees, which is pretty darn decent. In fact, it's terrific. So it's not a bad antenna, and getting it up a half wavelength on 20 meters is about 35 feet, so you can do it. That's pretty good. So it's not a bad antenna. Now, how does the beam compare to the dipole? Again, one of our magic charts that Bob and I put together is this one. And again, we compare the dipole to the beam, and the upper right is the dipole gain at beam maximum radiation point. Anyhow, as you can see, the beam does pretty well, even when it's low. A 40-meter beam at 20 feet is not too bad. It has 6.93 dBi, and maximum gain is at 54 degrees, which is pretty good. And if you have a dipole up that high, it's not quite as good. You're losing about 2 dB. Notice the impedance, though. It really gets affected by the height, which is an issue that you all have to be aware of when you're putting an antenna up. It goes from 29 to 42. It's not as bad as a dipole, but it's bad enough. At a half wavelength, though, look at the numbers we're getting. They're pretty good. If you have a 40-meter beam at 70 feet, you've got a pretty nice antenna. It's got 10.88 dBi. The maximum gain angle is 26 degrees. The front to back ratio, which is the amount of signal going out the front versus how much squeaks out the back, is 12 dB, which is 2 S units. And the impedance is really close to 50 ohms. The dipole is quite a bit less. So you're comparing it to the dipole, you got about 4.5 dB less off the dipole. So it's a pretty good antenna. So you can see that there's some advantages of a beam over the lowly dipole, but not as much as you might think. It's only going to have about 3 dB more gain in the forward direction, which is just equivalent to doubling your power. At 0.15 wavelengths up, the beam has 2 dB gain and 6 dB front to back advantage over the dipole at the same height. That's pretty cool. At half a wavelength, the beam has 3.18 dB gain and at least 2 S-unit front to back advantage over the dipole at the same height. What that means is the signals you don't want to hear are down 2 S-units, while the signals that you want to hear and that you want to be heard from are basically equivalent to doubling your power or doubling the transmitter, the receiving signal's power coming into your rig. A beam or a dipole half up on half wavelength is what we talked about earlier, and all the data that we show say that's a good place to be if you can do it. And then even at 0.15 wavelengths, the takeoff angle is 46 dB lower on a beam than a dipole, which means you can, at all heights, you're better off with the beam for DX because it drops the angle of maximum radiation by several degrees. So if you're working stations, though, within 100 miles on the lower bands, and you got to cover a lot of territory, a dipole up less than a half wavelength is better than a beam or vertical. So if you're worried about something for ARES local within, for example, a state, within 400 miles, 400 miles out, it starts to change. But 100 miles, it's really good, which is what we have in Massachusetts. Half wavelength or less is better than a beam or a vertical. So the question is, where do you use what? And that depends on what your mission is. So you got to think about it a little bit when you're putting up antennas. So now we'll get to the DBI comparisons. Somebody can tell you, and I've seen some ads like this, they say they compare the gain in dBi in free space of the antennas with whatever you're dealing with. Well, you know that if you put a dipole that has 2 dBi, 2.15 dBi gain over the isotropic antenna, you put it on the ground, it goes up, especially in the angles where you want it to be and at the levels you want it to be. At a half wavelength, it's a darn good antenna. It's got quite a bit of gain. So you got to ask the question, when you're giving me a message, tell me how high the antenna is, not just what the numbers are in free space. Free space doesn't depend on the reality called ground. So the third thing the next thing we've learned is these 3 issues. The dipole impedance gain and resonant frequency, they depend on height. So your antenna, actually, if you take a dipole and raise it way up in the sky and then bring it back down to the ground, you'll find that the resonant frequency will drop. The lower you go, the lower the resonant frequency will go, and that's because of the effects of end effect. And Bob and I wrote a little article on this that's on our website, ocfmasters.com, and you can read that if you like. You can go on there and find it. So the answer is yes, Virginia, your dipole has gain even for DX, especially at a half wavelength up. So the answer to the question, does your dipole have gain? The answer is, of course it does. So we'll go for questions now.
Okay, everybody's on mute, so just press your space bar and you can ask questions.
There's Allison.
Okay, I think we're working. When you talk about beams, 2 elements is maybe 40 meter, may be common, but when you get into 20, 15, and higher, 3 or more elements, those takeoff angles improve even at low altitude considerably. You know, the classic case of mirrors and lenses. The more glass you use, the finer the beam. And in the case of antennas, the more elements you use, the finer the beam. And the ultimate goal, of course, is to be flat on the horizon, but that's difficult to do. unless you get up into UHF and many, many, many tens of elements or more.
Yeah, that's right, Allison. That's quite correct. And the point I make, I take that point down to 40 meters again for our beam that we use on field day. That's why when we put it up, I try to say, let's get it up 30 to 40 feet, because then the takeoff angle is just about what we want to do to work. Since we set it west, we want to work the country, and it's got a beam width of about 90 degrees. So we can work the whole country if we set the thing west. And the angle that we have and the extra gain we get is much better than a dipole at the same height. And that's exactly right. But if we could put another element on it, well, that's another story. It's a little more complicated for 40 meters. Yes, it gets really big.
Okay, Bob, if you've got a short antenna, say a loaded dipole, how would that affect your patterns and gain?
It depends upon how long the antenna is. And there's no way I can generalize on that easily. It depends on where the loading coil is and all that. But it does affect it. And
Yeah, work I did with compact antennas at the office back when, if you don't get too ridiculously small, the pattern remains the same. The gain, however, goes down due to losses in coils and matching.
can I turn this off since I don't think we need this? How do I stop sharing? Okay. Now I can see people. Yeah, that's right. It's hard to tell what the pattern's going to do. I mean, what the gain is going to do, because
It's also going to impact the bandwidth.
yeah, it will affect the bandwidth too.
Yeah, because my antenna on 40 meters, it's 18 feet long, but I do manage to work out with it.
Yeah, one of the interesting things is for antennas smaller than half a wavelength, they still have pretty much exactly the same radiation pattern. So all of the energy is going in the same way, even if it's theoretically very, very small. So as Allison said, it's really just the losses. That's one of the curious things. As the antenna shrinks, the gain of the antenna doesn't go down because the directivity is the same. It's just being able to match it and use it becomes much harder. Quite a conundrum.
And then their bandwidth goes down. That's the problem.
The bandwidth only goes down because of the matching issues.
Right.
The actual antenna radiates the energy in the same place.
Yeah, sure. All you have to do is just match it and get the energy to it.
That's all you have to do, right?
Yeah, I was on a ship at one time, and George will know this one. And they had about a 15-foot mast, and they ran it to a tuning network, and they grounded it, of course, to the ship. And they were running that all the way on frequencies from 3 to 30 megahertz.
Yeah.
Because they could tune it. It worked just fine.
Yeah.
But of course, the feed line length was about 1.5 feet. So, right into the transmitter. So it was not much loss. It worked pretty well.
I did some work on submarine antennas, which were limited in height, so they didn't have a big radar cross section. And surprisingly, the losses were still very high because the submarine resistance to the salt water was relatively high compared to the radiation resistance of the antenna at the low frequencies. So, yeah, you can't beat physics.
Well, the other thing is that if you're going to load an antenna, you don't want to load it right at the base if you can help it. That's where the losses are the greatest.
That's where the current's highest. Yeah.
Yeah, you want to put the load up higher, or you want to put a top hat on it.
Yeah, the key element to any loaded antenna is keep it as big as possible. Half size compared to a standard dipole is not terrible. But when you get down to 1/4 or 1/10, you're mostly heating coils and any other matching devices being used.
Actually, that's a really good point, Allison, because with a lot of us have these automatic antenna tuners these days, and they can actually match the losses better than the antenna sometimes. And you think you get a good match, but you're actually not matching the radiating part of the antenna.
Yeah, that's true.
George, do you hear me?
Somebody else have a question? I heard somebody talking.
That was Bill.
It's Bill. Am I being heard?
Barely hear you, Bill.
Yeah, never mind that. I won't make my comment. I still can't be heard.
Turn it up. I turned the volume up. Go ahead.
Oh, I was out in the garage today and I discovered a pair of crutches that I had when I injured myself a few years ago. They've been sitting out in the garage and I measured them, and it turns out that each crutch is a quarter wavelength at 6 meters.
Perfect.
I think I can make a nice rotatable dipole for those old crutches. Any thoughts on that?
So,
That'll work.
so crutches are resonant on 6 meters. Nice to know.
Think about it, a meter and a half is about 5 feet. And if you extend it all the way, the crutch is about 5 feet.
If you put them the large end outward, it almost emulates a bicone. It's a very wide band antenna.
Yeah, that is. Yeah, I'm just going to say that. That's a good idea.
Nice and easy to match.
I think Bill wants to talk about this at the next meeting.
If it works, I'll let you know.
Dare we wish that he breaks a leg? I do have a question for Bob, which is hopefully not redundant. And although it's right up there in the stupid level, for Bob and Bob. I thought that a dozen years ago or so, reading about contesting and DXing, that there was some takeoff angle below which it was at least not worth fretting about, if not a bad idea to pursue. That if a takeoff angle that's too close to zero was, for most QTHs, for most transmitter locations, not worth pursuing or a bad idea. Does this ring a bell? And have you ever heard of it? And do you recall a rule of thumb?
Usually it's the lower the better, but on the other hand, you can only get so low. And
We've got a beam width, and if the beam is intersecting the ground, I would think that would pick up noise and disperse the energy and such.
Yeah, I wonder if it could. Who knows? Maybe it was a rule of thumb for the size of the average hill, and New England is going to get in the way. So don't fixate on trying to aim at the hill.
Well, there is, for any specific situation, a magic angle that if it's too low, you're going to just go smack into the side of the hill, like you suggest. For most cases, though, the angle you're really interested in is not relative to the ground, but to the ionosphere at the distance that would be most useful. You know, if you want to hit people 3,000 miles out, you want to get a bounce of 1,500 miles, give or take, and so on. The other extreme is at mid VHF and up. If you're doing satellite or specifically EME, angles below 5 degrees and approaching 0 degrees are very desirable, because then where your signal goes is more directly related to where you've bore sighted the actual boom. In other words, are you really looking at the moon, or as the influence of the ground, especially if it's on the horizon, push the beam up above the moon, so to speak? Things like that come into consideration. For practical HF work, though, that's cutting it way too fine.
Thank you all.
This is K1 JVD Bame. So Bob's, I'm kind of suspecting you have strong opinions on NVIS antennas from what you said, but there's always the perennial debate whether you should put the second wire under NVIS. Do you have any thoughts on that?
it's unnecessary, but you can do it. You're really going to be more affected by the ground itself.
So it has no relationship to being a reflector.
Well, it will be a reflector, but you're fighting against the reality of the fact that you'll get a pretty vertical signal without it. You're talking about fractions of a dB.
yeah, the other aspect of that is you have a very lossy substrate around that wire because it's laying on the ground or extremely close to it. And it's probably not optimally spaced with the antenna to get the up angle that you want. In the end, it's a lot of effort for low productivity.
Right, fractions of a dB.
Okay, thank you very much.
As I said, when I was running the net control for ARES, my antenna that I was using was about it was on 75 meters. It was about 50 feet up, and I was being heard by everybody. And it was down to the Cape, up to New Hampshire. It was just fine.
Yeah, it's important to remember we're in New England too. When I was operating out in the desert near in the Arizona desert in Texas, there's not much ground reflection. It's just dry rock. So a piece of wire makes a big difference there. Here in New England, we're blessed with usually wet ground very close.
They even have water under it.
Well, one of the other considerations is for NVIS exclusive operations. A good example is I run 75 meters for an antenna that's all of maybe 12 feet above the ground, 3 meters, 4 meters. And it's a convenience consideration. And yeah, the feed point impedance is a little lower, but being lower to the ground, it's also shorter, and it fits within my property then. That makes a difference. It's little things like that are part of the compromises of designing and building and installing antennas. As it turns out, at 12 feet, it's a very effective antenna out to about 400 miles. It's not terribly directional. I talked to guys down in Connecticut and out in New York and Ohio even. But, being 12 feet up, it's very easy to fix if a branch falls on it.
There is that. The maintenance part is very important.
Okay, are there any more questions then for the two Bobs?
I was just going to follow up with a comment on all that, which is it also points out how fretting about height, is 5 foot more, if anything like that, helpful. Becomes almost working it to death.
Say that again, Allison. You broke up in the middle of that.
I was saying that based on that and other experiences, the height you put your antenna at is optimal, is what you can do. And fretting about 5 foot higher or 5 foot lower is probably not going to make a hill of beans. It's wasted energy fretting over something.
Good point. I was going to make that point. Thanks. Bob should have reminded me. We were talking about that yesterday, the day before yesterday. That the difference in height really isn't. It's you're dealing with fractions of a dB. It doesn't make any difference at all. And fractions of an angle. I mean, the angle may go from 45 degrees to 42 degrees. It doesn't make any difference.
So if you're real DX hunter, you'll have antennas at the same antenna at different heights, so you get different takeoff angles. Optimize every last straw. Fun and games, folks. Lots and lots of wire.
And lots of money. Yeah, I know people who do that, and they wind up with 100-foot towers with antennas at 1/3, 2/3, and then at the top. And, at $5,000 an antenna, it's a pretty expensive operation just to get the tower plus all those antennas up and rotating. But that's beyond my capability.
Okay, any more questions then? So I'd like to thank the two Bobs for giving us this enlightening lecture here, and also put in a plug for them. If you haven't read it, go out and get the current issue of CQ and read their article on the antenna for 40 and 15. And I'm glad to see you're getting more articles published. So give us a heads up when they're coming out, and we can get the votes together to get you the cover plaque award too.
Yeah, I never thought about that. Yeah, sure, do that.
Okay.
Yeah, there's one in the January issue. It's coming out.
Good. So let's see. I think Alan is ready with our finance report. So let me turn things over to Alan here.
I'm not even going to be sharing screen.
Okay.
Chauncey, I intend to send the complete report out to the mailing list tonight. So don't freak over transcribing facts and figures. On the finance side of things, since the last virtual part meeting, we took in $105, spent $47.64, and also took in $10 into the repeater fund. Actually, today I took in $65 in dues and $5 in additional repeater fund stuff. But strictly speaking, period to period, we're up $67.36. At the end of the day, we have $7,116.10 in the general fund, $5,720.49 in the repeater fund, and $1,269.25 in the kit fund, leaving a total of $14,105.84 in the checking account. Over the calendar year 2020 just ended, let's see, overall we took in $3,138.50, spent $738.94, netting us $2,399.56. And in particular, the repeater fund went up $886.85. On the human side of things, I have unacknowledged dues payments from K1PAK, Peter, a new member, Doug, KC1IOK of Lancaster. By the way, John Forrest renewed, WB1HBE, and he has moved, he and Elaine have moved to Fitchburg. And I just realized he said he moved to Fitchburg to get a bit more house for the dollar and space for the grandkids to visit. And I had written it down as he'd moved into the Bitmore houses. I just realized what he meant. I have unacknowledged renewal from Dave WI1R, unacknowledged renewal from Doug KZ1CY, unacknowledged renewal from Steve KA1IKK. Let's get this straight. A new member, Mark KC1DST of Stowe, unacknowledged. And another new member, Harsha, now Kilo 9 Zulu Hotel Victor, I checked, of Westford. He was recently, well, it was a KC call, but he ditched that for, if anyone has previously heard KC1 Oscar Hotel Oscar, he's now a K9 1x3 call.